Okay, in addition to multiplying by a constant, we also have a convenient rule. It's where if we have multiple types of functions, and they are being added or subtracted, the functions, we can take the derivatives and add or subtract the derivatives to get the total of the derivative. So we're picking up now in 2.2. So what I mean by that is, what if we have more complicated functions like f of x equals x cubed minus 4x plus 5? What we can do is take the derivative of each one of these pieces separately. So the derivative of x cubed is 3x squared. The derivative of negative 4x is just negative 4, which is negative 4 times the derivative of x, which is 1. And the derivative of 5 is 0. So in total, our derivative is 3x squared minus 4 for this complicated function. Similarly, if we have some awkward terms, the same principle applies. So to take the derivative here, we'll take the derivative of negative 3x to the fourth, which would be negative 3 times 4 times x cubed. The derivative of here, 1/2 times the derivative of x squared, which is 2x. And now for this last one, this is 3x to the 1/2 power, so the derivative here will be 3 times 1/2 x to the negative 1/2 power. So in total, this will be negative 12x cubed. My 1/2 and my 2 here will cancel, so this will be minus x. 3 times 1/2 will be 3/2, and x to the negative 1/2 can move to the denominator. So that will be, our total derivative here will be negative 12x cubed minus x plus 3 over 2 to x to the positive 1/2 power, which is really the square root of x. So as you can see, our more complicated functions can have somewhat complicated derivatives, but our strategy is still the same. Similarly, if we're dividing, we can do things like splitting all of our terms and taking each derivative separately. This would be 3x plus 2 minus really x to the negative first power. Take each derivative separately. So this is 3. The derivative of a constant is 0. The derivative of x to the negative first would be negative 1x to the negative second. So in total, this would be 3 minus a negative is plus, x to the negative second. But we might look at that as 3 plus 1 over x squared. So these derivatives, doesn't matter how many things are added or subtracted together, the mechanism is still the same all the time. Now, we don't just have functions, though, with powers of x, or roots, or rationals. We've encountered in the past different kind of functions as well. So let's start with our two most basic trig functions and talk about their derivatives. So the derivative of sine of x is cosine of x, and the derivative of cosine x is actually negative sine of x. You're just going to take my word for it for these. For the other 4 trig functions, we will find out their derivatives in the next section, but we're going to start with these two, because if we recall, the rest of the trig functions are based off of these two. So once we have these two in play, and some other techniques for multiplying and dividing, which we will do in 2.3, we can get the rest of them. Now, the same rules for the constant and some difference apply to trig function derivatives as well, or adding and subtracting. So the derivative of f of x equals 2 sine x. Again, the 2 just comes down, and it's times the derivative of sine x, which according to the rule is cosine x. So the total derivative here is 2 cosine x. What about b? F of x equals 3x squared minus 2/3 cosine x. Again, I can do these derivatives separately. The derivative of 3x squared is 3 times 2x. The derivative of the negative 2/3 cosine x, we leave the negative 2/3 multiplier there. The derivative of cosine x is negative sine x. So that means my total derivative here would be 6x plus 2/3 sine x. And I think leaving C for you to practice is a good choice. It's not super different, but I do want to give you an opportunity to do one yourself. And I know there will be homework assignments where you get to practice this plenty, but it never hurts for you to try it on your own to confirm that this works. Now, as a reminder, the derivative represents the slope or the instantaneous rate of change. And a common use for it is to describe objects in motion, particularly things moving in a straight line. In the past, in algebra, you've likely talked about the position of maybe an object that was launched into the air and then it's falling to represent its height, or possibly something rolling on the ground, its position. Now, these functions generally have always described the position of an object relative to time. Now, what is the instantaneous rate of change of position? Well, it's how fast you're changing position at any one point in time. Normally, when we talk about how fast you're changing your position, we're talking about speed, or more specifically in physics, we talk about velocity. Speed is usually has a direction. Velocity could be positive or negative. Speed is always positive because it's like moving 48 meters per second to the right or 48 meters per second to the left. You have those denotations for speed, but for velocity it could be a positive 48 meters per second or a negative 48 meters per second if you're going to the left. We also know that the equation for defining the position of a falling object is negative 1/2 gt squared plus v naught t plus s naught, where g is our acceleration due to gravity, which should be negative 32 feet per second in terms of feet, or negative 9.8 meters per second in terms of meters. Initial velocity will change depending on how the object is launched. That's what v naught is. And s naught is the initial position, which could be on the ground or it could be in the air. So we can do some word problems using this. So we may have a problem like, at time t equals 0, a diver jumps from a 32-foot platform at initial velocity 16 feet per second. After how long will the diver hit the water, and what is the impact velocity of the diver? Okay, so if we use that rule, we know that our g, our gravitational force, this is in feet, is negative 32 feet per second squared. We know our initial velocity here is 16 feet per second. And our initial position is the 32-foot height. So when I substitute those into the equation from the last page for our position, I will get our total position function, s of t, is negative 1/2 times negative 32 t squared plus 16 times t plus 32. Now I actually think, because the negative 1/2 is already out there, the gravitational force, 32 feet per second, should be positive in this case because they're already accounting for the negative. That gravity tends to make you fall. So I'm going to assume that they want the gravitational force to be 32. Normally I would just say it's 1/2 times the gravitational force, but since we're putting the negative 1/2 in there, it'll just be 32. But this simplifies to negative 16t squared plus 16t plus 32. Now what they want is when the diver will hit the water. That means when the height, or s of t, is equal to 0. Now lucky for us, these are all multiples of 16, but I'm going to divide by negative 16 because I would prefer my leading term to be positive. So 0 equals t squared. This will be minus t minus 2. And this is just a simple factoring problem. 0 equals t minus 2 and t plus 1. So either t equals 2 or t equals negative 1. Only one of these should make sense. Time should be positive. He shouldn't be hitting the water before he launched himself. Now, why is this helpful? Well, if I wanted to find the velocity, all I have to do is find the derivative of the position function, this one. The derivative of this is negative 32t plus 16. And all I would have to do now is plug in my time to get negative 32 times 2 plus 16, which is negative 48. And this should be feet per second. It would make sense, right, that his velocity is negative, because chances are when you're diving into water, you should have a negative velocity because you are going down. And this is really all that we're going to do for 2.2.